Hello students, now in class 11th, I will tell you the some kinds of oscillations. Here I will tell you about the forced oscillations or driven oscillations, then damped oscillations, then free oscillations, and then I will tell you about the resonance. So first I am taking the forced oscillations. Forced or driving oscillations. Let when an oscillator oscillates under the effect of applied periodic force, its oscillations are called forced or driving oscillations. Oscillations. The body, the oscillator, oscillates continue to oscillate till the periodic force is working. When periodic force is off, then there is no oscillation. If periodic force stops, the forced oscillations will be had. So now we can have the example of this one. Suppose we are having this support, and these are suppose two strings here. This is a string, or this is simply a strip like this. This is XY, and it is having a pendulum. This is the pendulum P, and this is pendulum Q. This is the strip. When this P is slightly disturbed from its mean position and left to oscillate, then after some time this Q also start to oscillate. Since the force on this Q will act because of this P via this strip XY. So on this oscillator, the following three kind of forces act. When P oscillates the Q oscillator will start to oscillate due to force acting on Q via strip XY. So this is allowed to oscillate, then this will also oscillate after some time, and this will oscillate because some force will act on it. So until this continue to oscillate, this will also continue to oscillate, and as it stops, this will also stop. So the pendulum P, the pendulum of the oscillator Q, having the dragon oscillations. The oscillations of Q oscillator are forced oscillations. So the following forces act on the Q oscillator. Number one, restoring force. F1 equal to minus Kx. Number two, damping force. F2 equal to minus lambda V. Lambda equal to constant, V equal to velocity of oscillator. Here K is force constant, and third, applied periodic force. F3, this is equal to F naught sin omega t, where F naught is the amplitude of force F3, where F naught equal to maximum force. So the total force So total force F equal to F1 plus F2 plus F3, and this is equal to F1 is equal to your minus Kx, this is equal to minus lambda V, and this is your F naught sin omega t, and this force F is equal to m d2x upon dt square. So we can have this d2x upon dt square plus k upon m plus lambda upon m into v equal to f naught sin omega t. Now this is divided by m. So this we can have this d2x upon dt square plus this is omega square x plus this is your 2r into v equal to this is your f naught sin omega t. So it is the differential equation where this is your omega naught square equal to k upon m, and this 2r equal to lambda upon v, and r is called the damping coefficient. Damping coefficient, and f naught equal to f naught upon m. So this is the differential equation it is differential equation of forced oscillations. Forced oscillations. Now solution of this equation can be written the solution of differential equation this is equal to x naught sin omega t plus phi. Now you can see that this omega is the frequency of the periodic force. Omega equal to frequency of periodic force, and omega naught is the natural frequency, and this x naught, this is the solution of this equation, where x naught equal to f naught upon square root of ओमेगा नॉट स्क्वायर माइनस ओमेगा स्क्वायर का होल स्क्वायर प्लस 4r square omega square. And you can see that the amplitude, this x naught, where x naught is the amplitude. Amplitude. And you can see that this x naught is depending upon the frequency of the applied force, that coefficient, damping coefficient, and the natural frequency. So x naught depends upon omega and r. And from here you can see that in steady state, r equal to 0 means that we neglect the damping. Therefore, this x naught equal to f naught upon omega naught square minus omega square. And now this amplitude is depending upon this omega naught. And you can find from here this we can also write this x naught equal to f naught upon m omega naught square minus omega square. Now because we are having the square, this will cancel, so we are having the so much. There are three conditions. Number one, if omega is very less than omega naught. Omega is very, means omega naught is very high. Then x naught equal to f naught upon m omega naught square. So this is the amplitude when the natural frequency is very high in comparison to the frequency of the periodic force. i.e. the frequency of periodic force is very less than natural frequency of oscillator. The amplitude depends upon natural frequency. And now number two, if omega very greater than omega naught, omega very greater than omega naught, then x naught equal to f naught upon m omega square. Now we are looking from this point that when this is less than to this, then we are having this condition. So x naught is equal to so much, and when we are having this to be very small in comparison to this omega naught, then we are having this condition. So at this condition, this the amplitude depends upon the frequency of the periodic force. In this situation, the amplitude depends upon frequency of periodic force, applied periodic force. Applied periodic force. And third, if omega equal to omega naught, omega equal to omega naught, then x naught equal to maximum. Maximum, but not infinity, due to damping, because we have taken this factor to be 0 here in a steady state. So we can say that when we are applying this condition, then x naught will be maximum, no doubt, but it will not be infinity because of this factor. So if this is 0, then we are having this x naught equal to the infinity. If damping is 0, the x naught will be infinity, will be infinite. So now we can show them by the graph. This we can have like this. This we take now this condition when omega equal to minus x is equal to maximum, then this is called the resonance. It is called resonance. So we are having this the amplitude x here, and this is we are having this omega. This is the frequency when we are having this equal to so much f naught m omega square, and you can see that the curves is like this. This is equal to f naught upon omega naught square, this value, and then this is for very high damping. When damping is low, then we are having this. This is for low damping. This is for very low damping. If the damping is 0, then the curves will be like this. So this we are having the frequency, which is omega r, the resonant frequency. So this is very high damping. This is high damping. high damping. It is for low damping. And this curve is for very low damping. This is damping equal to 0. And this curve is very low damping. So you can see that as the damping decreases, the peak of the curves goes up. Clearly, as damping decreases, the amplitude increases. Or peaks of curves go up, and for damping is 0, the peak is at infinity. For 0 damping, the peak of curve is infinity. So this shows the variation of the amplitude with the damping, and we can have the energy of this oscillator also. The kinetic energy. And average kinetic energy. Are making this omega r where omega r equal to resonant frequency. Resonant frequency. So now this is the kinetic energy. On this side, this we are having the omega, and the curve is like this. This is omega r. This is the kinetic energy, maximum kinetic energy. Ke maximum. And resonant frequency, this omega equal to omega naught. this is not 0. And we can have that this energy of the oscillator we can have to this and that the oscillator in resonance condition the oscillator absorbs maximum energy from the source. So this is about the periodic force, this periodic oscillations, and there are so many examples of periodic oscillations. You can see all your musical instruments have the forced vibrations. Examples of forced oscillations. Forced oscillations. Your musical instruments. Musical instruments. You can see all kind of it's a violin or this your guitar and all the drums. They continue to produce the sound till they are beaten by some force. Suppose there is guitar and just like you want to produce the sound from that, then you have to shake the wire with the help of your finger. So till your finger will continue to strike with the wire, stretched wire, there will be the vibrations in it. And as soon as you stop your finger to strike with the wire, then there will be no vibrations at all. And also so many drums where till the drums is beaten there will be the sound and then it will stop. So this is also the example of musical instruments like guitar, violin, drums, and you also the organ pipes. This as you can have that the well of your school. So till the peon will continue to strike the hammer with the well, that will produce the sound, and as soon as he stops, there will be no sound at all. Sound produced by striking the hammer with the bell. Similarly, your electric bell also, till the electric bell is switched on, there will be sound. As soon as it stops, there is no electric bell. Electric bell, etc. So the all musical instruments in our life that we see, also your TV, radio, etc., they are having the force vibrations. So till there is the electrical force, then this will continue to vibrate, and that will produce the force vibrations. So these are so many examples of the force vibrations in our life. So now you all like, share and subscribe this video. Thank you.